다시 어나운스 해줄게. Okay. So this midterm will be the grade. The final of this midterm will be will correspond to 25% of the total grade, and final exam will be 35. And your group task is the most important one, and that will be 40% of your grade. But as I announced, this group task, each member, all member in one group will have the same grade. And group task 5, which I assigned last week, will be delayed and due on last day of October. That means after exam. Okay? Any questions on midterm? Okay. For those who didn't take course from me in the first semester of this year, I would like to go through the beam theory. Okay, I understand that those who didn't take a course from me didn't study anything about the beam theory. So today I'm gonna spend time to go through chapter 10 again. Last week I just went through very briefly, but I was requested to do one more time because many of you didn't take any beam courses. But again, chapter 10 is very important to understand the beam theory. But I'm always trying to compare between the theory between bar, torsion, and beam. There is a certain similarity. If you follow that flow chart, A+1, that will help you to understand whole together. So you study each subject, but you can understand them all together. There are two chapters on beam theory, chapter 10 and chapter 11, right? Okay, I would like to give you overview about this chapter 10 and chapter 11. What is the chapter 10 about, and what is the chapter 11 about? Okay. Very simply, beam is now, I think we have a problem. Simply, this beam is subject to a distributed load, which we'll call QX. Okay, QX. And the left-hand side and right-hand side is certain boundary conditions. So we do have a boundary condition at x equals 0 and x equals L. Let's call this is x equals 0 and x equals L. And another given condition is, of course, is a material properties, and including sections, dimensions. Okay, property and of course a geometry. So these are given conditions, and what we like to find is the how much it deforms. See, this will certain deformation, right? I will just say this is a center line. I will just say this center line will have a certain deflection curve. Originally, it was a flat. This is a before deformation. But at a certain point, each, let's say x, will have a deflections Vx. That is the what we want to have drive. And also each section, this is the a beam, okay, beam. And each section will have a certain sigma x distribution. So sigma x will be function of x and function of y. So in coordinate wise, this is x and this is y. So here is the to find deflection v as a function of x, and sigma is a function of x and y. Now, here is the given, and here is the to find. See, we as an engineer, we clarify what are the given conditions and what is the objective. What objective means what to find, what we trying to find. We want to clarify. This is called problem statement. And it's always a start to clarify this problem statement. Is okay? Okay, this is a beam problem. And now, to drive this equation, we first assume there is a moment just function of x. Forget about everything. I mean, forget distribute load and forget everything. We just want to have a moment x is a function of some angle. See, this one, when it deforms, it will have a certain angle, right? This is important to understand. This is a beam, and when we have a moment, this is a fixed. And moment, this will, look at my fingers. Finger originally was a vertical line, but when you have a moment, it has a certain angle, right? So this is the angle, and this, we want to have a relations and between this moment and this theta. This is the chapter 11. I mean, sorry, chapter 10. Now, chapter 11, we want to have relations between Qx, okay, Qx and moment x. What is these relations? That is all about the chapter 11. There is one missing part which was covered in chapter 11 is that theta, okay, this is a theta. Okay. A theta is a very, for small theta means very, is not like that, okay? Very small deflection, very small deflections. That is the a deformation we consider in beam theory in general. So theta is very small, and tangent theta and theta is the same, and this one is the same as the tangent curve. See, this is the Vx. V is a deflection curve, and derivative means is a derivative. This is a theta, and that is a theta, right? This is I mean, let's say we have a certain cross section here. So this is a theta, and that is a theta, and theta is a tangent theta. Tangent theta will be the theta, and this is the deflection curve. So it's something like that. This is the curve. This originally was a very flat, and we have a load Qx. It has a deflection, and Vx is a deflection curve. And derivative of a Vx is a simply theta. So here, this one, this is just one simple equation. That's it. And chapter 10, again, moment has a relation with this theta, and this theta is related to here. And now, this Q, chapter 11, we want to drive relation between this Q and moment. So combining all, I will give you a result, by the way, okay? The moment will be EI d theta dx. That is the one final equation out of chapter 10. And this one, again, I will give you a final result. And second derivative of moment, okay? Second derivative of a moment will be Qx. So this is the final equation, that is the final equations, and this is the relations. So we combining all these three, okay? This one and that, what do we have? Put this one into here. Then moment equal EI, and this is a theta, there's a theta, and now we have a twice derivative of a Vx. V is a deflection, okay? And this one, moment, second derivative of moment is a Qx, which is a load, and we put this into here. What do we have? EI V here twice and here another twice. So we have a 4 times derivative equal Qx. Okay, so this is the final govern equation which will governs this problem statement. As you can see that given load, the given will go here, and what we like to find is a V, and this V is nothing but governed by this fourth derivative differential equations. Okay, so sorry to say, but this subject will be covered in midterm. Okay, chapter 10 will be included in next week midterm. But not this whole chapter 11, we're not gonna cover, but chapter 10, which is about this relation, will be included in midterm. Okay? So anyhow, the reason I explain whole thing is that I want you to understand why we study about the chapter 10 and 11, and we will have a final equation, governing equations. Okay, so let's go to chapter 10 in detail. And this is a very typical, again, a flow chart for any structures. It also applied to a beam. It was applied to a torsion as well. Remember that. And in torsion and beam, for the beam, as I mentioned, in chapter 10, forget everything. We just focus on just one beam, and beam supports moment at each end, or this is equal to a fixed, and here same L, and apply moment. So in this reaction force to be in equilibrium, we will have this moment. So this one and that is the same thing, right? So just a fix and you apply moment. And here, what we like to find is that we like to study what's going on here. To do so, this will be like that. Okay, this is the what's happening. And very importantly, pay attention to here. Look at this vertical line. Look at this vertical line. What happens? This vertical line simply rotates, right? See, that's the very important observation. How much it rotates? This much. That much rotation is the same as this. So this theta and that theta is the same. So in chapter 10, our concern is that when we apply a bending moment, how much it rotates, or how much it rotates, the same thing. This rotation, or that rotation is the same one. So to study this subject, or what's going on in this beam, we have to consider equilibrium and stress strain and this deformation condition. But as in torsion, we start with deformation observation. You remember in the torsion, you start with a certain line here, and then it deforms like that, right? Like that. That was a starting point of a torsion, and similar to here, our observation start with the beam, the deformations, and which was a simply like that, and we simply like that, and this one it goes like this theta, and I will put this deformation into equations, and what equation will show us this kind of deformation. Once we have a deformations, okay, deformation, then strain can be always given, easily given in terms of deformations. And once we have a strain, we can always have a stress by considering stiffness. In this case, stiffness is Young's modulus E. And finally, equilibrium. What is the equilibrium? Well, we have a certain stress here. Stress will distribute a cross-section, and that will be will contribute to a moment. So moment, some moment and stress, and stress goes to here, and stress and strain, and sigma, epsilon, and epsilon has to be a deformation. We will drive that one, but that is the d theta dx times y. Looks a little bit complicated, but this one is the most important equation in this beam theory. As you can see, as long as we have this one, we put it here and we put it here, and then we can get the relation between moment and theta. That's what we want to drive in this equation, these chapters. Okay, please keep that in mind. And now we will go to these deformation conditions. Okay, here I explained a little bit about this deformation last week, but let's consider this deformation again. This is the before deformation. Before deformation, we have a beam. Now we apply moment on the right-hand side and left-hand side. Because of equilibrium, whatever we apply moment, and there will be reaction on the left-hand side, the same amount of moment. Now, what we can clearly say is that, let's take a look at the upper one. Upper skin, just a portion, little portion of the upper skin and lower skin. Look at that. Look at this guy, and what's happening here? This length or whole line, is it extended or contracted? Yes, it has a certainly contracted. It's in terms of strain, it's a negative, compressed. Am I right? That you can easily guess. How about the bottom one? Look at the bottom line, bottom surface, and this is the bottom surface. And is it under tension or compression? Yes, it is certainly tension. So one thing for sure is that top skin, top surface is the compressions, and bottom surface is a tension. We don't know how much, we don't know how it varies through the thickness, but one thing for sure is that a strain is the compression and tension. But one thing we need to clarify is that this one is a distraction. Okay, distraction is a compression, and this one is also nothing but distraction. So please remember, this is extraction. The strain we are considering is axial strain. So whenever we have a certain like that, something like that, this top skin is a contraction or compression, but here is the tension. That is the one thing we have to keep in mind. Okay? Now, what we want to move on to achieve is that, okay, it's too complicated. I'm going to delete a little bit more. Okay. Now, I will call calculation of strain. We just observed how on the strain in the top surface and bottom surface. But what we like to do is to calculate the strain as a function of y. Y means through the thickness. So for that purpose, let's consider a one line. This is a before deformation, by the way. Before, and this is after. So this AB line is located at Y. Well, this line is Y equals 0. We don't know the position yet, but we just say this is a certain line is Y equals 0, and this AB is located, and distance from this line to Y equals 0 is simply Y. So let's take a look at what will happen to this AB line. Well, for that purpose, let's take a look at the whole regions, and the whole region will deform like that. And what we observed was that this line is a compression compared to this, and this one is the tension compared to this. So this AB is after deformation. Okay, this is after deformation, and very importantly, let's call A prime B prime. So this is the A after deformation. So by definition, epsilon x, okay, epsilon x is the A prime B prime, that's the after deformation, and AB is this line before deformation divided by before deformation. That's the definition of a strain, right? So the key point is that what's the length A prime B prime? Well, back to here. See this line is Y equals 0. And this Y equals 0, we assume that this line, when it bends, it has the radius, okay? It radius, and let's call that is the R. R is the radius from this center to this Y equals 0 line. So every point, once we deform, every deformed shape is passing through one common point, and which is the center of radius. So this one, so again here, this is the line, and that is again, let's call R. R, we don't know yet, but what we know this moment we apply, but we don't know how much R. But R is the amount which represent how much it bends, right? Very important value, R. So this one is the Y. What is the length A prime B prime in terms of R? Let's take a look at A prime B prime, because this is the Y and this is R. So center, the radius from here to there is the R minus Y. Actually, this is the Y, right? R minus Y. And now, as you can see, that is all d theta. So this is all d theta. So this length, we can say this length is simply r minus y times d theta, right? That's the length. And another one is the before deformation, AB. Before deformation is the length, this one, right? But how can we represent this AB in terms of R? Well, this one is simply same as that one. And this line is the same as that line because this line does not extend, does not contract. So this line, the radius wise here is the R. Again, d theta is everywhere, is a common angle. So this one is the R times d theta. So before deformation of the A prime, B prime is AB. AB is simply R times d theta. Okay, this is the most important observations. And divide by R theta. And now you see theta all disappear, d theta, and R is disappear. Let's take a look at what is left. Minus y R minus y and R. So please keep in mind that R epsilon x in this direction, okay, this direction as a function of y, is that function of y is R 1 over R. 1 over R, let's call it K. Before deformation, it was, what was R? R was infinite, right? Before deformation. Originally, R was infinite, so curvature was 0 before when we apply. Now when we apply moment, it gets smaller and smaller and radius will be smaller. So inverse of R, curvature will increase and increase, right? So this way we can see that curvature is related to a moment. But anyhow, please, this is the final observation in deformation, minus y curvature or minus 1 over R. Another important geometric relation is that what is the R times d theta? Please take a look at R times d theta. What is that? This distance, right? We already know that. But this distance is the same as what? Dx, right? Dx. So R times d theta is nothing but dx. So here comes very important equation. 1 over R will be d theta over dx. D theta dx is the 1 over R, and which is defined as a K. Okay, please keep in mind, K, 1 over R, d theta dx is all same physical meaning. So, but here, what is the theta? That is the important. Theta, again, is here, we have, this is a theta, okay? This is a theta, and section we will rotate. So to rotate, it certainly rotate like that. Cannot rotate like that, okay? But when you rotate, it automatically lifts up, lifts down. And this one makes this theta. So this theta is the same as this theta. So epsilon x, okay? Epsilon x is a minus k, minus y k, actually should be a curvature, kappa, but I just call k for simplicity. Kappa is a more accurate name. Minus y curvature minus curvature is 1 over r, which is the d theta dx. Okay? So in chapter 10, and this is the very important, the most important observations, and here, see, minus epsilon x is the d theta dx and y. That is the what we derive from this, a simple a deformation observation. See, this one is the theta angle, and that is the theta, and the center line we have a r, and r. So again, 1 over r will be curvature, and this will be d theta dx. So d theta dx or curvature or 1 over r, this basically caused by what? What do we apply? Actually, moment, right? Moment we apply, and which will cause this much d theta dx. So moment is the force, and deformation is d theta dx. So all this next step is toward driving relation between moment and this d theta. I will write down the curvature for your better understanding. D theta dx is the one we're gonna drive through this strain and stress and equilibrium. Okay. So now let's drive this one. What is the next step? Once we have a strain in terms of that, again, here, unknown is this guy. Unknown is d theta dx. D theta dx. We don't know the theta, okay? To calculate the stress in this section, okay, we have a certain stress distribution. We don't know yet, but certain stress, sigma x, is a function of what? Through the thickness means y, right? So this sigma, just to calculate the sigma, we just multiply Young's modulus. That's it. And so we get the stress. Now, when we have a stress at cross-section here, and by definition, we do have a moment. So basically, moment will cause this stress and strain has these relations. So basically, put everything together, finally, we will have a moment and d theta dx. Okay, that's our target. And I already shown here, but let's see how we get this one. So next step is again very simple. You apply Young's modulus to epsilon x. Epsilon x, we do have this one. So sigma x is the d theta dx. As I mentioned, 1 over r is d theta dx. Okay? Okay, so just take a look at how this stress distribute. Well, since the strain is just linearly varies through the thickness, well, simply the sigma x will also linearly varies like this. But what we don't know is how much this magnitude. In other words, let's go to a next step, and this one is the final final one. See here in cross sections, we do know these relations, and strain is like that. Whatever stress we have over the cross sections, say we have a certain area dA, which is located y from the center line, and we apply certain stress sigma x here, and sigma x times dA. What is that? This is the A force, which is located at distance y, right? And this dx times dA is a force times y will cause a what? Moment with respect to this line, right? So there will be a moment in z directions. So moment z is the sigma x, dy, and y. That is the what? Equilibrium equations in cross sections. Equilibrium equation at cross section. Again, cross section, there is a certain moment and certain stress, and this stress was caused by moment. So we are using a moment, an equilibrium, a relation between moment and sigma. Okay, so this is basically equilibrium equations. Now, what all we have to do is to put this sigma x here, and epsilon x we already know. So put this here, here, here. Now, so sigma x, what is that? E epsilon, okay, no problem. Now, what is the epsilon x? Minus y d theta dx, no problem. But look at that, there is a y here, there is a y here. So we have a twice of a y. And Young's modulus and d theta dx. And remember, we have an integration over dA. dA is the over the cross sections. Integration over the all A. Okay, now we are approaching to a final equation. See, when you integrate, Young's modulus is a constant over the A, and d theta dx is nothing to do with cross sections, so we can, these two terms can come out of this dA. What is left in this integration is that y squared dA. What is it called? This is called bending moment of inertia, right? Bending moment of inertia, simply we call IZZ. IZZ. So this one, E IZZ, and d theta dx. This one is the final equation. See, moment equal, I will put, write down EI and d theta dx. d theta dx, or this is what? K, or 1 over R. It's all same thing. Well, simply you can say moment equal EI K. See, that was the one we want to obtain. As I mentioned at the very beginning, right? CEI d theta dx. So this is the final equation in this chapter 10. And this chapter 10, this is very important, and let's try to compare between shaft and beam and even bar, simply say okay, let's consider one more final. See, d theta dx is that in terms of a length, here from here to there is a length L. So d theta dx is the uniform. So we can say L divided by L, and final angle is theta 0. So theta 0 divided by L will be simply d theta dx. Okay, so d theta dx. So put this one into here. What we'll have is that theta 0, okay, theta 0 will be a moment L, moment times L. See, this d theta dx is a theta 0 divided by L. So theta 0 will be moment L times EI. Now, please remember this equation. Angle theta 0 is the how much it rotates. Equal moment L divided by EI, which is very similar to a torsion. You remember torsion? When we apply torque T, how much it rotates, right? The angle of rotation is phi. Do you remember the final equations? Phi equal torque T L divided by G IP. And compared to this equation, they're pretty much same. So here are the comparison for the beam. See, the load is the bending moment, and moment of inertia is by definition y squared dA, and deflection in this case is the angle of rotations. So here we have a moment and fixed, and it rotates like that. So this cross section rotate, and this is the theta, and that is the theta. I will call it theta 0. So theta 0 is the moment L divided by EI. And for the shaft, under the torque, I will call T. And in this case, polar moment of inertia is R squared dA. And compared to this, very similar, but except R here is we have a Y. And angle of rotation, phi, in this case, a shaft, we have a clamp and we have a torque, and you have angle of rotation, phi, how much it rotate. Phi is T L divided by GIP. Compared to this, quite similarity, right? So instead of T, M, L, L, G, E, IP, and IZ. And even compared to a bar, where this bar is subject to a force F. So force, we have a Fx, and now delta FL divided by AE or EA is all same. So for the cross section, this is the one, and here and there. And stress is simply divided by force divided by A, but torque, tau shear stress is a torque divided by I, but this is proportional to R. And this. And everything, as you can see here, 3 structures, has a common similarity, right? Any questions so far? So,
질문.
yeah.
그 I 오멘팅 분식 I에서 이제 인테그랄 y 제곱 dA인데 그 y가 이퀄 엑시스 기준으로 y잖아요. 그러면 그냥 네모 말고 다른 모양에서 어떻게 이퀄 엑시스에서 어딘지 어떻게 볼 수 있는지.
Okay. Well, very important questions. This question is that how do we decide y equals 0? Okay. How do we decide y equals 0? Actually, this slide is all about that. Okay. So now, how do we decide y equals 0 positions? Well, rectangular, something like this rectangular, well, very easy to decide. This will be just a center. This will be half h. This will be another half h. I mean, total, say h. And for the rectangular, it's easy. The position of this y equals 0. But how about the other cross sections like a triangle or some other things, and some cross section in general? How do we decide it? For that purpose, very important equilibrium is that, see, we do have this sigma x is a function of y, but and this will corresponding to a moment, right? But we do not have any fx, because we do not extend any forces. We only apply this one, right? So this axial force fx, by definition, sigma x times dA has to be what? 0. Because we didn't apply any axial force, so summation of a sigma x over the cross section should disappear. So sigma x, we do know this relation, so we put it here. And then we integrate here, when we integrate E and R is a constant, so it has to be 0. So now you can see that integration y dA has to be 0. What is y dA? So from this, y equals 0 should be determined. So we have a whatever cross section, where will be y equals 0? Here or there? Where? We do not know. But what we know is that wherever we have a y, this y equals 0 should make cross-section integration. Integration of this cross-section should be 0. Do you know the definition of this? Which axis would makes this one is a 0? Any line which go through a centroid, say this is a centroid, this is a centroid. So any line passing through centroid would make this integration equal 0. right? So it's clear that the neutral axis should pass through the centroid. Okay, that's the final conclusions. So in triangle, where is the centroid? This is the 2 to 1, right? 2 to 1. See, physically, why 2 to 1? See, when we have this triangle, imagine that this triangle, and then there will be a certain stresses here. So this area will be under compression, and this area will be a tension, right? So this compression and tension summation should disappear, right? So summation should disappear. So if we do have a more area than top, this distance has to be smaller. So by definition, that gives us the centroid. Okay. Okay. So I'm glad you asked these questions, and it's.
만약에 그런 모양에 따라서 무게 중심을 지나는 물체를 만약에 여러 개 물체가 복합적으로 있을 경우에는 그때도 똑같이 저식을 만족해요.
Right. Yes. See, that is another high-level question. Very important, advanced topic. Say this is the A material, B material, A material. This is the beam. And now we have a certain moment. Where is the neutral axis? See, this one, no matter how many different material, how many material have, always this one should disappear. So if you put it here, and this E, Young's modulus, is no longer constant, because this EA, EB, EA, they are all different, right? So it has to be inside, and you can come to a certain relations. That's how you decide where is y equals 0. Okay? Yes, it's, if we have a different material, the equation will be a little bit complicated. For example, say we have a, say this is in terms of a magnitude, and this is the E twice of a 0, and this is just E0, then neutral axis, I will put one such problem is we have two material, different material here and there. Okay, say this is twice of the bottom stiffness wise. Then even though this thickness is the same, okay, this is the same, but the neutral axis, where will neutral axis exist? Top or bottom? The neutral axis should exist top. Why? Because this area, even though it's small, we have a huge stiffness, right? So you will have a lot of stress compared to a bottom part. So that force will be a 0. See, one thing very important is that regardless of this multi-material stacked, always epsilon x is the, no matter how many material, no matter one material we have, always proportional to y d theta dx. Okay, always linear. Strain is always a linear. So if we have a very high stiffness top, this neutral axis will goes up. I mean, you don't have to calculate, but you do need to understand the concept, okay? Just qualitatively. Again, this final equation is only for a beam with one material. Now, one typical problems which I can assign in your midterm is something like that. Oops. Say we have a beam, and what we drive was that, say, given L and given EI and under the moment and how much it rotates, right? But let's say we have another beam attached which has a different bending stiffness. So E1, I1, and L1, and this one is the E2, I2, and L2, and then we apply a moment. Now, what we like to find is the how much this guy is rotate. Well, so how much it rotates? Phi, I will call phi2. See, this one, it has a certain rotation and certain rotation. Let's call this is a phi1 and phi2. And how much will this phi1? Okay, this is very typical problem for the beam case. Well, it would be easier to understand. I mean, if you compare between, we have a very similar shaft, not the beam, and on the torque. And here we have a GJ, GIP, I mean 1, and L1, and G2, and P1. This I, P, and I is different, right? This is a polar moment of inertia, and L2. And now when we apply T2, I mean T, and the question is the how much it rotates, angle phi. And this one you can easily solve, very similar to a task number 4, right? And simply you can see that each one, and this first one is this is a torque, because this torque, and from equilibrium you have a torque. So this is a torque, and there is another torque and T. So this torque and all the same. And here is the same thing. This moment and moment and moment will be the same, right? So from this, how much it rotates? Well, we know that T L1 and G1 and IP1, and this one angle, actually in this case, phi2 minus phi1, because it's a relative angle, will be a torque T, L2, and GN, and IP2. Okay? So, you can practice solving this kind of problem. Well, you can easily expand one shaft, two shaft, and three shaft, And even for the beam, the same thing. You can have 1 beam, 2 beam, and 3 beam. And remember, you have a group task. And what did you have? You had many shaft, and then you have a clamp, right? So you apply a torque and torque and torque and torque, and very similar. This one and that is the same problem. Only difference is that, see, this one was a torque, and this one is all torque is the same. But here, since we applied a T12 and T23, so this T1 and T2, they are different, right? There is a certain another terms which was applied to torque at the center. I mean the connection point. Okay, so anyhow, they are not exactly same, but a structural understanding is pretty much same for all structures. I mean, whether shaft or beam, or even, you know, when we have a bar, 1 bar, 2 bar, and 3 bar, and then you apply a peak. Or even you have a spring 1, spring 2, spring and 3, you apply force. And how much it deflect, how much it deflect, or how much it rotate, or how much it rotate. All structurally same concept. Only difference is the meaning of a force. When you have an extension, deflection is the delta. When you have a torque, deflection is the angle of rotation. When you have a bending, deformation is this angle. Okay, so it's very important to understand the concept of the force and concept of deformation. So this one, you can see that all concept is F equal Kx. No matter what, even spring or beam, torsion, all F equal Kx. See, but here we had moment equal K. Oh, sorry, it's a BK, okay, Kx. See, this one is corresponding to K, some stiffness. So this is the deformation. And here, torque is a GJ and dphi dx. I will call instead of a K, I can say the theta dx. And for this bar, we can say a P equal is simply EA what? UX D U dx, right? So as you can see here, all same concept, EA, EI, and GJ. And this guy, that, and that is all corresponding to a deformation concept. And this force, moment, T, and F is the same concept as F. And stiffness, okay, stiffness is the EI or GJ or EA is all corresponding to a K. So if K is a high K, what does it mean? If you have very high, it does not extend, right? Resist to deform. So if you have a high EI, very high GJ, high EA, it resists to deform for the given forces. So I hope that you understand in general is a force and deformation and stiffness. Okay? And even though we have a many spring, even though we have a many shaft or bending, and even though we have a many degree of freedom means that not only this is the x, but this can be another x and another x and another one, right? And even here is the torque and torque and torque. So in this case, this is the F and K and X. So this will be F1 and F2, and this will be X1 and X2. All, so you have many series, structures, and we have a node, and each one you have a deformation and torque. Always we have, if you have a n beam, number of beam is n, one number of torque, shaft is n, we have a n by n equations. So this is just, you don't have to solve it again, but just for your reference. For given task like that, you have always a torque, and that is this one. And each point you have a deformation, you have this, and all you need to have is to get K. So, but anyhow, this is a generalization of structures. Okay, so that's the what I'd like to cover today. And any questions? Again, the subject we cover will be included in midterm, and midterm. Again, I will like to say. I like to say that midterm, the subject we will cover will be this flow chart, and for the bar, for the torque, shaft, and for the beam. And before that, we importantly stress-strain relations. You remember stress-strain relations? You know, this guy, 6x6 equations. Okay, so this was a task number 2, right? You have many multiple and apply, and you have a certain geometric condition, and you have to have this relation which governs a certain body. But in bar and beam and shaft, we only has one dimensions here. This and that. That is for the bar and beam and shaft. But in general, we have a 3-dimensional body. All the stress and strain, they have to have a 6 component, and this is the relations. If we have a thermal term, temperature increase, this is the one we have to consider. Well, okay, that's the all we want to say. After midterm, we will go to a chapters of beam, thin wall shaft and advanced beam theory, and also buckling and energy method, which will be covered in the after midterm. Okay, any questions? If no, okay, all the best luck to your midterm, and which will be on next Wednesday. 7 o'clock, and I will announce the room. And most likely this room and then some other rooms. Okay, so thank you, and see you in 2 weeks or next week. Oh, sorry. Yeah, we do have a class tomorrow, and it will be in class. I mean the online class. Okay, online class. Tomorrow is online class. Okay, you don't have to come here. There will be Zoom class.